Any questions about this? Okay. The video is out there. I tweeted it last night about 10:30. So I don't think my cats made it on this one, but they might. You might hear my cats. They were helping me. If you don't hear them, they were there. We've got like 11 cats. I know. Not kidding. And 4 dogs. We have a big house, so.
I'm done with the dogs.
Yeah.
You know, if you die in your house, your cats will eat you.
Okay. She said if we die in our house, our cats will eat us.
Your dog will lay there next to you and starve to death.
So, one last chapter we need to cover is this one in this unit. I bought it at Lowe's yesterday. I brought my Farmer's Almanac. Okay, because we're talking about weather forecasting, and actually this is a valid thing. There's something called the long range forecast. Okay, I kind of bookmarked what we should be having for today. But you know, why do you care about the forecast? Well, if you're like me, you need to know what to wear in the morning, or whether to put your dogs out, to keep them out, or whether the roads are going to be bad, you need extra time, that sort of thing. Of course, there are hourly forecasts and there are daily, like a 10-day forecast. The hourly ones are more accurate, right? The going out 10 days kind of changes as we get closer. Sometimes you're like, drat! Sometimes you're like, thank goodness it changed, right? So there are practical reasons for wanting to know the weather aside from what to wear. So for instance, like if you're NASA, you need to know what sort of cloud cover you're going to be running into. I'm not sure that I don't know if they worry about cloud cover, but they would lightning, okay? That sort of thing. And I think historically farmers really kind of need to know kind of when to get in there with the temperature, when the temperatures are warming, or if there's going to be rain coming, they need to get their crops out, that sort of thing. So yeah, there's an assortment of reasons why we would care what the weather is going to be like tomorrow or 10 days out or a month out. So when it comes to weather forecasting, of course you're probably familiar with the National Weather Service and NOAA, okay? So National Weather Service we think of as more like local. National Weather Service actually reports to NOAA. We're going to talk about these things called initial conditions, or what the atmosphere is right now. And a few things. Okay, one is that, and I'll bring the globe up because we're going to need it. One is that we are all in this together, meaning this world of people. If we want to know what our weather's like, we actually need to kind of know what the initial conditions or what the condition of the atmosphere is basically everywhere. Okay, so we're going to see actually there is a world organization network that does that. So you see another acronym, NCEP, stands for National Center for Environmental Prediction. Lots of acronyms. A lot of this is actually done, like not so surprising, by computers. It's kind of cool. We'll talk about something called the numerical forecasting, and hopefully you'll think computers because that's what does that. Okay. But the folks that we get it from is the National Weather Service. This private sector, I don't know if that would be like WeatherBug and the Weather Channel. That's private sector folks. Okay. And as far as I can tell, those folks are trying to make money, right? And they have the access to the same initial condition information that the National Weather Service does. One of the things I'm excited this semester is there's a link. There's a website out there that tells you how good they do. You're like, well, how accurate is that forecast? Well, there's a website out there that tries to kind of compare all the different forecasts, including the National Weather Service to WeatherBug and the Weather Channel. So I think that's kind of neat. So NOAA. I think that's the way, actually it says National Weather Service. So the National Weather Service is under NOAA, okay? And then National Weather Service also has the folks in Norman, Oklahoma that give us our watches, right? The Storm Prediction Center. And when we saw the video on Friday, the guy was at Florida issuing hurricane information. So that's the National Hurricane Center in Florida. So a lot of folks are into this, involved in issuing forecasts. So this is the worldwide sort of folks, okay? The World Meteorological Organization. And not so surprising, they turned to the UN, which doesn't necessarily have to do with weather, but the folks in the UN, United Nations, represent the globe, right? Those are the same folks that are part of this World Meteorological Organization. There are 3 centers for this World Meteorological Organization. One is here in North America, and it's in Washington, District of Columbia. And then there's one in Moscow, and then there's one in Australia. Okay, so there's 3 of those. So those would be just another important link in the chain. Okay. So they all work together. So at the top here, if you want to write the word instead of current atmospheric conditions, if you want to put initial conditions, that's usually what I call them. Initial conditions. And basically, it's the current conditions, but the reason I call them initial conditions, here in a minute when we turn to our computer and we say, computer on. No, we say, computer, what is going to be the forecast for 3 days from now? We're going to have to feed this to the computer, okay? So there's different ways to get initial conditions. This actually is one of those buoys that's out there in the ocean, okay, collecting temperature and maybe wind, and yeah, you can see that's wind data from those aerovanes, pressure, okay? But there's all sorts of ways to get initial conditions. Some we've already talked about. Okay, so those initial conditions need to be fed to your computer. Put another way, the forecast your computer spits out is only as good as the initial conditions you give it. It cannot come up with a forecast in a vacuum. So these are really important, kind of an assortment. I have a slide again to talk about weather balloons, okay, to kind of remind you what those look like. And then I have a slide that's going to talk about kind of these satellites that orbit the Earth. So as far as land sources, here's North America, okay? There are, of the 10,000 land sources worldwide, 1,000 or 1/10 of them are right here. And actually, you've already seen them, okay? They're basically, to me, they're your ASOSs, oftentimes. And I have another picture to remind you what ASOSs look like. So these are basically oftentimes run by the FAA, because the folks in the airports need to also know this information. Okay. So these ground or land data sources can record a bunch of stuff. And again, oftentimes like the ASOSs, they're recording it digitally and just sending it remotely to whoever wants to know it. Actually, the airport up here, I think when we talk about ASOSs, the airport up here has a live feed where it's updated like every 20 or 30 minutes. You can actually see what that ASOS is reading. So these are all important things to feed our computers, initial conditions. So here's your ASOS. They come in kind of different sizes, different shapes, but you can almost imagine as you're going from left to right what each one of those little gizmos is able to tell us. Okay. Well, it tells you a rain sensor, temperature dew point sensor, precipitation identification, wind tower, wind speed, data collection package, I'm not sure. Looking at cloud height, the ceilometer, freezing rain sensor, and visibility sensor. So they're not all like that, but that's kind of an example of what an ASOS would look like. Pretty cool. Weather balloons, we talked about weather balloons way back when, but just to kind of remind you, they go up twice a day. So rain, it's worse than the mailman, although the mailman's out there I feel bad for mail people. I'm like, dude, that is so terrible. But anyway, they go out twice a day, the same time worldwide, as far as I can tell. The ascension is where actually it's taking the data. And remember, as it ascends, it's got that little box, okay, and it's taking in all sorts of information. If it also gives you wind speed and wind direction, that box is what we call a Raw sound instead of just a radio sound, okay? And so it takes 2 hours going up. and then the latex in the weather balloon gets big and big and big, and it like pops, and then there's a cute little parachute that lets the thing fall down, and I think it doesn't take any data on the way down. Unlike those drop wind sounds for hurricanes, right? Okay, so another thing that the National Weather Service or the Meteorological World Organization count on are these satellites. Not only are they just like spy satellites, right, but they are satellites that are giving us good information about the condition of the atmosphere. And there's two types of satellites, and they depend on how they orbit the Earth and how far above the Earth they are. So the first type is this one, the polar orbit satellites. And so basically they're low, okay? They're closer to the Earth than the other type, and they go around like this, okay? So from pole to pole. And of course the Earth is rotating. So here's the deal. The slide says, you know, these are great if you're after information about the poles, but because the Earth is spinning, they're kind of random with regard to what latitude they're going to hit if you're in the middle latitudes. The Hubble Space Telescope is one of these. I know it's not a satellite, okay? It's a telescope that's looking out that way, okay? But it's also kind of in one of these low polar orbits. And the Hubble Space Telescope, and anything that does this, takes about 90 minutes to go around, okay? So if you're one of these that likes to see the Hubble Space Telescope at night, kind of see it flare up, if you wait about 90 minutes, there'll be another pass. Now, whether you'll be able to see that pass or not is another thing. Okay, but that's kind of how that works. The other type of satellite is not from pole to pole, but it actually orbits around the equator. Okay, and the other thing about this satellite is it's farther above the Earth. And the reason it has to be farther above the Earth has to do with the kind of the physics of the orbit. Okay, you've heard of decay orbits and that sort of thing. It can't be any closer than a certain distance. But the cool thing about this is the word geostationary, the word stationary and geostationary might give it away. Geostationary satellites, and I went ahead and showed the other part of this. A type of geostationary satellite is what we call our GOES satellite, GOES. GOES satellites would be geostationary satellites that are just ours, affectionately known, GOES. There actually is what we call a goes west and a goes east, looking upside down. Now the thing about these is the stationary part is that as the Earth spins, and I can't do both of this, but as the Earth spins counterclockwise, right, they hover. So their orbital time is the same as the Earth's rotation. Okay, so they hover over a particular location. That's the stationary part of geostationary satellites. Okay, so like I said, we have a goes west and a goes east, and actually you can look at these out on the internet. Again, kind of, I think every 30 minutes, they update the scans. So it's kind of cool. See if you can see us, maybe, no, maybe not. Okay. So those satellites, whether they're the polar or the geostationary satellites, what they do is they take these scans, okay? So wherever they are, remember they're hovering, they basically go take a whole series of scans, okay, and then they rest, okay? They take another series of scans. And there are typically 3 types of scans I'm going to show you. And the way they get these different is basically by looking at different wavelengths. Remember we said that light information comes to us in different wavelengths, like red is one color or blue is one color. And I know we talked that actually there are energies in wavelengths that we don't see, okay? Thermal energy is kind of after red, kind of a little bit longer than red, and we don't see it, but it's there, okay? And then there's actually stuff shorter than blue, invisible light that we don't see. So to get one of these 3 different scans, I'll just put them up here. Here's your 3 different options. So these goes west and goes east satellites are giving us these 3 images routinely. So if you go on the internet and look at what the goes has got going, okay, it will show you a visible image, it will show you an infrared image, And then it will show you, those are two different wavelengths, and then it will show you image where it used different wavelength, and it's just selected for water vapor. Not clouds, water vapor, water gas. Okay? So a few things, now I hope this makes sense. If that clock is the sun, okay, if that's the sun, okay, and if my satellite is over here, okay, the nighttime side, I'll go ahead and put North America over here. Okay, my visible satellite cannot see that stuff because basically this is what's lit up by the sun. Okay, as the Earth, as this comes to dawn or whatever, okay, now actually it can start taking visible pictures. I think that's kind of interesting. The other two pictures, as I understand it, images can be taken at night. So infrared, when we talked about infrared before, I think we said heat. Whenever somebody says, that's a wavelength that infrared, think heat. So actually that's what it's getting a heat signature. The water vapor is water vapor. So I've got a couple of images here. This actually was taken by your GOES 8 that's hovering over a certain spot. And this is a visible image. This is infrared, and this is water vapor. The infrared and the water vapor were taken the same time. So the thing about infrared, I told you, when you think infrared, think heat. Okay, this kind of reminds me of, there was like that. I can't remember the name of the movie, but where that the critter actually used infrared to anytime something. What was it called?
Predator.
Predator. Thank you. Yeah, I think of that. Doesn't that look like a predator image? So actually, the red in this case is cold spots. So you're like, all right. So what happens is when the chunks of air rise, they expand and actually they adiabatically cool. And so those are looking for cool spots in the cloud. And then that's water vapor up there on the right. Kind of corresponds with what you're seeing with regard to cold cloud tops. So when we talked about different scales of wind, we talked about microscales, we talked about mesoscales, like local winds, and then we talked about planetary scales. And I think when we talked about planetary scales of wind, we might even use the word synoptic scale. So synoptic maps, synoptic weather maps, are kind of a look at a large portion of land or a large portion of the earth. Okay? It's like the slide says, it's a snapshot of what the current conditions are. And remember, those current conditions can come from ASOSs. They can come from, did the slide say something about actually even airplanes that are flying like back and forth, they have to carry passengers? You can equip them with measuring devices that can tell you stuff. Okay? They can come from those sort of things. So these synoptic weather maps in the past have been drawn by hand, but now we rely on the computers to kind of knock them out. This is an example of what a synoptic weather map would look like. A large area, again, current conditions. Do you guys recognize the one on the left? It looks like a mid-latitude cyclone. Yeah, in its mature stage. I agree. So synoptic weather maps, current conditions. So when we talk about weather forecasts, I'm actually going to talk about some types of forecasts that you guys can do, okay? But in general, this numerical weather prediction or numerical weather forecasting, you need computers, okay? And you're going to have lots of numbers coming through for your computer. The other thing, though, about your computer is equipped with a program or a model, okay, when it talks about program or model. And somebody designed that model, usually specific for kind of your location, to kind of anticipate how Mother Nature would behave based upon just how Mother Nature behaves based upon initial conditions. So you need those models. Okay. So I think Weather Underground does this in some of its places. When you look at Weather Underground, it actually will let you pick which model you want. Okay. And because a different model will give you a different forecast. It's like, dang it, which one's right? I don't know. So sometimes I've heard it described that the weathermen kind of know have an instinct for which model to go with, when to go with it.
I heard the guy on Channel 10 talk about it, like, there's some models out there that are putting us, are low at 30, but I don't think we're gonna get that low.
That is so cool.
Like, he talks about different models giving him, but his model he thinks is more correct, of course.
Yeah, I don't know if you heard what Autumn said, but the meteorologist actually will kind of discuss when he's presenting the weather, this is my thinking behind this. There are assortment of models that I can see, but I'm going to go with this. I don't know. It's tough.
They think theirs are the best, of course.
Yeah.
Everybody thinks their model's the best.
Yeah, they probably all think that their model's the best. So now you see this word initial conditions that I had you put on the slide a few slides ago. So initial conditions are what you feed your computer. Okay. So when you feed your computer those initial conditions, before you feed them that deluge of, oh my gosh, tons of information, and I bet there's programs to do this too, you basically filter out what you're coming in. A lot of times we do that with data in the lab anyway. Like if you have an outlier, you're like, dude, that so is not right. Well, then don't give it to the computer. Okay, so that's kind of like a smoothing process. The other thing that can be done before you feed stuff to your computer is you can try to kind of estimate between holes, where there's holes. Notice I'm kind of putting my hand over the ocean here. Not very many weather balloons going up there. Not any ASOS stations. So when it comes to understanding what the conditions are around the world, we have holes. So you can kind of do some smoothing there too. But let's just say you come up with a set of initial conditions that you want to feed to your computer. You've picked out your program or your model, okay, and you're ready to feed it. So, feed me. So what your computer does is this. It basically says, if this is my time, it's increasing from left to right. It says, all right, this is now, okay, and based on what you're telling me and the program you told me to use, I can tell you what the condition of the atmosphere will be in 2 minutes. That's what your computer's telling you. You're like, dude, can you do better than that? So what the computer does then is it says, yes, I can. I'm going to assume I'm right for 2 minutes, and then actually I'm going to take those and I'm going to plug them back into that same program, and I'm going to spit back. Now this is done really quickly, right? Not much time is left at all. It's like, yeah, I'm going to plug those 2-minute forecast in as initial conditions, and I'm going to come up with a 4-minute forecast. I'm like, can you do better than that? So yeah, I'm going to assume I'm right in 4 minutes. I'm going to plug those in as initial conditions, and I'm going to come up with 6 minutes. Any better? Okay, 8 minutes. So basically it just kind of assumes it's right and goes on as those initial conditions and plugs it back in. Now, these are a lot of initial conditions, even to get to 2 minutes, and it's a complicated program. So this is a lot of computer power. But that's kind of what they do. They kind of piggyback forward like that. So, yeah. If you're going in 2-minute segments, it takes a while to kind of chunk that out, especially for so many different locations around the United States. Now that I think of it, we're lucky that we have things like AccuWeather and, the Weather Channel, because if we could only rely on the National Weather Service, and I'm going to show you their accuracy, we might be kind of frustrated, okay? So those folks are using their own computers with the same set of initial conditions, as I understand it. So these models, right, these models that you feed to your computer so you can go ahead and give them initial conditions and it can crunch those. These models, actually, the idea of using a mathematical model was somebody came up with it, I can't remember his name, back in the 1700s, okay? Like, that is so cool. It's like a physicist, like physics, But the problem was that if he hand calculated all of his stuff through his mathematical formula, it would take, I don't know, a week to come up with tomorrow's forecast. Not very practical. But he had the right idea, so computers need to really make this numerical forecasting work. So progs, or prognostic charts, are those ones that your computer spits out. But kind of like we were talking about up here, what your computer spits out isn't necessarily what you're going to see forecasted on your nightly news, okay? Because the person who issues the forecast can kind of put his or her own spin on it bring their own knowledge to the table. They might use these model output statistics to kind of curb what forecast they're going to put out from the progs. I think that's kind of cool too. So numerical weather forecasting or numerical weather predictions use computers and initial conditions. Okay. So what could go wrong with computers, right? We're going to talk about why forecasts are incorrect, right? And actually, these are two of the reasons why forecasts are incorrect. Those programs that they chose to use or whatever, even though it tries to mimic Mother Nature, it really can't speak entirely because Mother Nature has been known to throw some twists. Okay, the atmosphere doesn't behave as they thought it would. And those initial conditions that we got from the ASOSs and all that, there's some uncertainty in that stuff too, even though you try to smooth the data before you put it into your programs. All right. So speaking of, there are some issues with your initial conditions, okay? This is kind of where this leads in. There's a pair of things called the butterfly effect and chaos. Sorry about that. So those two things actually make it kind of work together to basically say when your computer gives you a forecast, it might have issues with it. What the butterfly effect says, if you've watched the butterfly effect movie, basically it says, well, I'll choose South America here, okay? And the butterfly effect actually came, as I understand it, from a meteorological origins. Basically says, say you have a cute little butterfly down there, flaps his or her wings, it disturbs the air. According to the butterfly effect, it changes the weather here. Whether it flaps its wings or doesn't flap its wings, and how it flaps its wings has effects here. That's the butterfly effect. Now, does that really work that way? You're like, I don't know if I really believe that. But that's the butterfly effect. And it kind of just says that small things have big consequences, and that's what the movie kind of said, okay? And, you know, they add up, you know, a bunch of butterflies. Now that would have an effect. The other thing is chaos, and chaos is like a sciencey thing. Chaos says that, well, I'll get away from that. But according to meteorology, in this context, what chaos is saying is every measurement that was sent in to stick in your computer has a little bit of uncertainty in it, okay? And that little bit of wiggle room actually can have effects on what the forecast may or may not be. So to kind of show you the butterfly effect and chaos, okay, the idea how it works. If we look at just one variable, temperature, okay, of course we need temperature, wind speed, wind direction, pressure, you know, cloud ceiling, you know, we need all that stuff, but just pick on temperature. Of course you have a thermometer doing that, and every thermometer has what we call a tolerance. So if we look at a thermometer that has a tolerance of 2 degrees, okay, that means it's plus or minus 2 degrees. Let's say it's setting at 32, your tolerance is 2, so that means you actually have a range of possible real temperatures from that thermometer working correctly. Your real temperature could be anywhere from 30 to 34, okay? Now, the best you can do is plug in 32, okay? But could it be 30? Yeah, okay? Could it be 34? Yeah. And so the problem is if it's 30 or if it's 34, then you're talking about some kind of effect on your forecast, okay? So that's just reality. That is just reality. So one way to get around the butterfly effect and the effect of chaos, the fact that there's actually uncertainty in all those measurements is this. It's called ensemble forecasting. And if you've ever played in an ensemble or sung in an ensemble, basically you have a bunch of people that are all doing it together. And that's what ensemble forecasting is. It's not a bunch of people doing it all together, but basically what you do is create a bunch of weather forecasts. So that's the ensemble part of it. These, and I'm going to show you an example here in a minute, but these bunch of weather forecasts are all forecasting for the same period. Okay? They should look the same. But the catch with this ensemble weather forecasting approach is what you do is you change the initial conditions just slightly, and you're going to get a slightly different forecast. So then what you do is you come up with your set, and I'm going to show you an example here in a minute, that has like 50 different boxes, and they're all forecasting for the same place, for the same location, same time. And you look for a pattern, and if you see a pattern, that's the one that you put forth. Okay? So in this sort of approach, things can shake out, such as problems with a particular forecast model. So the example I'm going to show you was Christmas Eve in Europe. So if I imagine the Europeans are kind of like we are, that one of the things they want to know about their forecast is, are we going to have a white Christmas, right? This is Christmas Eve. Okay. The other thing about Christmas Eve around here, a lot of travel, right? Okay, Christmas Eve, not only do you want to know, oh, it's going to be white, but oh, am I going to get to grandma's house, right? So the thing is it went this way, where these two boxes are what they put out. This is their forecast. And the way you read their convention is you can kind of see the maroon, the red, and the blue, or the maroon, kind of the pink and the blue. That's actually the precipitation, okay? They said that that's kind of what the precipitation would be. Those lines are isobars, so they're not very tight, okay? They kind of thought, you know, you might get a white up here, but... So that's what they forecasted, and this is what actually happened. So a few things. You notice it's very colorful. They got more precipitation than they forecasted. And the other thing is you can kind of see the tight isobars. So they had some nasty wind that they did not forecast. So hindsight is 20/20, and I guess this would have been in hindsight. But here are the little boxes, and I think there are 50 or so. Yeah, 50. These are 50 little boxes that, going back in time, you know, forecasting for Christmas Eve, each of these boxes represents a forecast with slightly different initial conditions. So what the point here would be is I'm going to circle ones that kind of show this pattern, yes. Now, is this overkill? Maybe. I mean, it would take a while to knock these out, okay? But just kind of to my kind of untrained eye, yeah, there's another one, isn't there? 21. I kind of see.
That's the same shape coming down.
Mm-hmm. That is very much the same shape. You can definitely see the color showing precipitation and that sort of thing. So again, hindsight's 20/20. So this is just an example where ensemble forecasting would have come up with a different different forecast they would have put out. So NWS, National Weather Service, okay, they received their prognostic charts and forecasts from the NCEP, which stands for National Center for Environmental Prediction. That one's earlier in your notes. Okay. So the folks at the National Weather Service, or on the private sector, as I would imagine, folks at the Weather Channel or in telecast, or they will wade through the prognostic charts and forecasts they get from the National Center for National Center for Environmental Prediction? Yeah, Environmental Prediction. Okay. And put something forth. All right, so here's where I have some, like, bloopers.